So, good afternoon. Uh, Today we are going to study the frequency response analysis in module 4. So, there we have to find the correlation between time and frequency response. That second order systems only we need to find. So, the frequency response analysis in that. Um, so, we already aware that there are standard testing signals used to study the performance of control system, that is impulse, step, ramp, parabolic and sinusoidal. Out of this, sinusoidal signal is the most important one. Most of the signal available in nature are of sinusoidal type. The response of the system may be time response or frequency response. For time response, input may be impulse, step, ramp or periodic. But for frequency response, input must be a sinusoidal. Now, when you are considering a linear system with a sinusoidal input is R of t is equal to A sin omega t. The steady state output may be written as C of t is equal to B into sin omega t plus pi. Now, what is frequency response? The definition of frequency response: the magnitude and phase relationship between the sinusoidal input and the steady state output of a system is termed the frequency response. The magnitude and the phase relationship between the sinusoidal input and steady state output of the system is termed the frequency response. In linear time invariant system, the frequency response is independent of amplitude and phase of the input signal. Now, the frequency response test on a system or a component of normally performed by keeping the amplitude, input amplitude A fixed and determining the output B and pi for a suitable range of frequencies. The advantages of frequency response analysis as follows. The signal generators and precise measuring instruments are readily available for various range of frequencies and amplitude. The easy and accuracy of measurement is another advantage of frequency response method. Wherever it is not possible to obtain the form of a transfer function of a system through analytical technique, the necessary information to compute its transfer function can be extracted by performing the frequency response test on the system. The fourth one, the design and parameter adjustment of the open loop transfer function of the system for a specified closed loop performance is carried out somewhat more easily in frequency domain than in time domain. The effect of noise, disturbance and parameter variations are relatively easy to visualize and assess through frequency response. If necessary, the transient response of the system can be obtained from its frequency response through the Fourier integral. The drawback of frequency response methods are as follows. For the system with very large time constant, the frequency response test is cumbersome to perform, as the time required for the output to reach the steady state for each frequency of the test signal is excessively long. Then the frequency response test obviously cannot be performed on non-interruptible system. So these are the drawbacks. Now we will come to our exact topic of under the syllabus: correlation between time and frequency response. Now, for a second order system, we will consider it. The standard form of the transfer function of the second order system shown in figure. So C of s divided by R of s is equal to omega n square divided by s square plus 2 psi omega ns plus omega n square. So a second order system represented here, R of s, C of s, kv s into tau s plus t1, that is equal to R of s here plus minus omega n square divided by s into s plus 2 psi omega n cs. When you are calculating cs by rs, you will get omega n square divided by s square plus 2 psi omega ns plus omega n square. Now, the sinusoidal transfer function of the system is instead of C of s divided by R of s is replaced by j omega. Then C by R j omega is equal to T j omega. Wherever s in the above equation, that is to be replaced by j omega. So omega n square here, j omega square, then 2 psi omega n s j omega plus omega n square. Dividing the numerator and denominator of equation by omega n square, we get, you will get it as 1 minus omega divided by omega n square. Here j omega square become j square omega square, that is equal to minus omega square. That is here minus omega by omega n square plus j 2 psi omega by omega n. This j will come here. When you are substituting, subtracting, dividing omega n square, 1 omega n is here, so that is cancelled. So you will get 2 psi omega by omega n. Now putting omega by omega n as u, here omega n as omega n, where u is the normalized driving signal frequency, we get T j omega as 1 divided by 1 minus u square plus 2 j 2 psi omega by omega n again u. Now the magnitude is obtained by m is nothing but 1 divided by square root of a square plus b square, that is 1 minus u whole square plus 2 psi u whole square. Now angle of T j omega is equal to pi, that is equal to minus tan inverse of 2 psi u divided by 1 minus u square. So imaginary part divided by real part. Now the steady state output of the system for the sinusoidal input. So now you got the magnitude as well as phase. Then the steady state output of the system for a sinusoidal input of unit magnitude and variable frequency omega is given by, then if you are writing that C of t is nothing but magnitude, that is 1 divided by square root of 1 minus u square all raised to square plus 2 psi u all square sine with the omega t minus pi. Omega t minus pi is tan inverse of omega t plus pi. So omega t minus tan inverse of 2 psi u minus 1 by u square. Now from the equation of m and q, equation of m and q, that is 7.5, 7.4 and 7.5, it is seen that when u is equal to 0, m is 1 and pi is equal to 0. Then when u is equal to 1, then m is equal to 1 divided by 2 psi and pi is equal to minus 90. And when u tending to infinity, m is tending to 0 and pi is equal to minus pi. If you are plotting that, you can see that when u is equal to, this is u, x-axis is u and y-axis magnitude. When u is equal to 0, m is equal to 1. Okay, at the same time, when normalize u is equal to 0, pi is equal to 0. Then when u is equal to 1, when u is equal to 1, m is equal to 1 by 2 xi, and if xi is equal to 0.707, you are getting a graph like this. And if xi is less than 0.707, then you are getting a graph like this. As u tending to infinity, xi, this m reaches to 0. Here, when u is 1, you will get it as the angle is minus 90, and u is equal to infinity, pi is equal to minus 5. Pi is equal to minus 5. So this graph you can easily understand. It is in page 441. Okay. Now the frequency where m has a peak value is known as the resonant frequency. At this frequency, the slope of the magnitude curve is 0. So the frequency where n has the peak value, that is known as resonant frequency. Okay, resonant frequency. At this frequency, the slope of the magnitude curve is 0. This slope is 0. Okay, let omega r be the resonant frequency, and omega r be the resonance frequency, and ur is equal to omega r by omega n be the normalized resonant frequency. Then dm by du, the differentiating dm by du. So here it is a 1 by square root of 1 minus u square all square plus 2 xi u all square. It is, you know that 1 by, you know the differentiation of that. So here dm by du ur is minus 1 by 2 denominator terms 2 into 1, the differential of this 2 into 1 minus ur square, and differential of this term, that is minus 2 ur plus this one, that is 8 xi square. It will be, if you are expanding this, 4 xi square ur square. So with respect to ur, it will become 8 xi square ur divided by the denominator, as it is raised to what it is, 1 by half square root. So it is 1 by 2 plus 1. So that is mean 3 by 2, that is equal to 0. So you can do the differentiation of this expression, that is this. Now it is equal to 0. Then you can see that anyway the denominator is not equal to 0, only numerator becomes 0. Then if you are arranging, this become minus 2 into 2, it becomes minus 4. Here it is 8. So 2 can be divided. So here 2, 4. Again 2 can be taken output. So you are getting it as 1 minus u square ur square minus into minus ur plus 2 xi square ur is equal to 0. So when you are multiplying with this and rearranging it, you will get it as, yes, and you are taking common. Here when you are multiplying minus ur into ur square, you will get minus ur cube. No, minus ur into minus ur square, you will get a plus ur cube. Minus ur into 1, you will get a minus ur plus 2 psi square ur. Then ur, if you are taking outside, you will get ur square plus 2 psi square minus 1 is equal to 0. In that you are getting ur square is equal to, this you are taking to the other side, 1 minus 2 psi square. Ur is equal to square root of 1 minus 2 psi square. In that ur is nothing but, ur is nothing but omega, ur is nothing but omega r by omega n. From that you will get omega r as omega n square root of 1 minus 2 psi square. And pi r is equal to minus tan inverse of square root of 1 minus 2 psi square divided by psi. Yeah. So you are getting like this. So when you are analyzing these circuits, you are getting the same response of this. Then expression for the bandwidth. Typical magnitude vacuum frequency characteristics of a feedback system is shown in figure 7.3. At the cutoff frequency, that means m is equal to 1 by root 2. So this is a typical magnitude of m, 0.7 that is the bandwidth. So then m is equal to the usual expressions. This one, u is changed with the ub. U is changed with ub. So when you are doing like that, 1 divided by square root of 1 minus ub square, 1 minus ub square all raised to square plus 2 psi ub square is equal to 1 by root 2. Then you are cross multiplying this and cross multiplying in this way. Then you are taking the square. Then you are rearranging it. You are getting it as u raised to 4 minus 2, 1 minus 2 psi square ub square minus 1 is equal to 0. It is similar to a quadratic equation. So minus b means 2, 1 minus 2 psi square plus or minus square root of b square b square minus 4ac divided by 2. Some mistake is there, but when you are doing like that, yes, there are, this 2 is not there. The square of it will come to 4ab. This should be covered like this. Okay, and then you are getting, when you are taking it, 1 minus 2 psi square plus or minus square root of 1 plus 4 psi raised to 4 minus 4 psi square plus 1. So ub is equal to, from that, this is ub square, ub is equal to square root of this term, the square root of that term. Okay, from that omega b is equal to omega n into multiplication this term, that is square root of this entire term. Now considering the step response of the system, the expression for the damped frequency oscillation omega d and peak value of mp for xi between 0 and 1 are as follows. Omega d is equal to omega n square root of 1 minus xi square. mp overshoot mp is equal to e raised to pi xi divided by square root of 1 minus xi square. Now, bandwidth versus damping factor. A normalized bandwidth mu b divided by a normalized bandwidth xi is equal to 1 by root 2. You are getting the bandwidth. Now, MR and MP, if you plot, you are getting like this. And another expression, the comparison of expression for the resonant frequency omega r of the frequency response and the damped frequency of oscillation omega d of a stress response. The relationship between these two, omega r by omega d is equal to square root of 1 minus 2 psi square divided by 1 minus psi square. The corresponding omega r by omega d plot versus xi, you're getting like this. Okay.